Welcome. Right now we are going to discuss the final module of 6th chapter in which we are studying surface integrals. In this module we shall study Stokes theorem and divergence theorem. In the last module we were introduced with the notion of surface integrals. The study of surface integrals will be continued in this module. Without going into much technical discussion, we shall now discuss a classification among the collection of all smooth surfaces. In the first collection, we consider planes, spheres, ellipsoids, cylinders, naps, that is half cones, etc. And in the second collection, we consider surfaces like Mobius strips. Let us imagine a rectangular piece of paper. If we glue the ends without twisting the paper, what we get is a portion of a right circular cylinder. On the other hand, if we first twist the piece of paper once and then glue the ends, the surface we find is a Mobius strip. Let us now select a point on a right circular cylinder and the outward normal to the surface at that point. Let us move along a curve lying on the cylinder and keep watch on the normal vectors to the surface at the corresponding points. If we return to the starting point, we can find the normal vector remains unaltered. But for a Mobius strip, the case is not the same. We may return to the starting point with the normal vector being oppositely directed compared to the direction when we started. The surfaces from the first collection are called orientable and those like Mobius strips are called non-orientable. Let us now state and prove Stokes theorem. Stokes theorem. Let T be a bounded region in R2 and sigma from T to R3 be a smooth, simply connected orientable surface. We further assume that first, the boundary del T, which we denote by gamma, of the region T is a piecewise smooth Jordan curve. Secondly, the map sigma from T to sigma T, which we denote by S, is bijective and the components of sigma has continuous partial derivatives at least up to second order on an open set containing T union its boundary. Let sigma gamma equal to C. Now, if PQR from S to R are continuously differentiable scalar fields, then surface integral del R del y minus del q del z dy wedge dz plus del p del z minus del R del x dz wedge dx plus del q del x minus del p del y dx wedge dy equals line integral over C p dx plus q dy plus r dz. In the above, the line integration over the curve C is performed along the direction which it inherited from gamma through the map sigma. That means we considered the curve gamma, now consider its image under sigma. Let us now consider the positive direction of gamma. So, it gives an orientation to C, we considered that. Proof. The desired relation relates a surface integral with a line integral. We recall that we can transform a surface integral into a double integral. Moreover, Green's theorem related a double integral with a line integral. So, this fixes our strategy for the proof. In the relation mentioned in the proposition, if we first put Q equal to R equal to capital theta, by which we denote the zero scalar field on S, then we find surface integral over S del p del z dz wedge dx minus del p del y dx wedge dy equals line integral over C p dx. Similarly, first putting R equal to 0 scalar field equal to P, and then P equal to Q equal to 0 scalar field, we find surface integral over S minus del Q del Z dy wedge dz plus del Q del X dx wedge dy equals line integral over C Q dy, and finally surface integral over S del R del Y dy wedge dz minus del R del X dz wedge dx equals line integral over C R dz. So, from 1 we can deduce all the relations 2, 3 and 4. On the other hand, if we add 2, 3 and 4, we get 1. So, the relation 1 is true if and only if 2, 3, 4 are simultaneously true, and conversely. Now, the relations 2, 3, 4 are similar, so proving one of them is sufficient for us. Now, let for all uv in T, sigma uv equals to x uv, y uv, z uv, and that lies in S. Now, surface integral of minus del p del y dx wedge dy plus del p del z dz wedge dx equals double integral over T minus del p del y Jacobian del xy del uv plus del p del z Jacobian del zx del uv du dv. This shows the theorem will be proved if we can prove that double integral over T minus del p del y Jacobian del xy del uv plus del p del z Jacobian del zx del uv du dv equals line integral over the boundary of T p dx. On the other hand, line integral over del T p dx equals line integral over del T p del x del u du plus p del x del v dv, and this equals double integral over T del u of p del x del v minus del v p del x del u du dv. Now, we combine the relations 5, 6 and 7 and find that in order to prove that the theorem, it remains to prove minus del p del y Jacobian del xy del uv plus del p del z Jacobian del zx del uv equals del u p del x del v minus del v p dx du. So, we start with the left hand side. At the first step, we write down the values of the Jacobians. So, we are left with 4 terms. Now, we can write them as del x del u times minus del p del x del v minus del p del y del v minus del p del z del v plus del x del v del p del x del u plus del p del y del u plus del p del z del u. So, this equals with minus del x del u del p del v plus del x del v del p del u. With this, we add and subtract p del 2x del v del u, and finally, this equals with del u p del x del v minus del v p del x del u. So, this completes the proof of the theorem. Let us continue the discussion of the above theorem. In the previous module, we deduced that if f equal to pqr be a smooth vector field defined on the surface S equal to sigma t, such that its components pqr are continuously differentiable at least 2 times, and small n equal to 1 by norm sigma u cross sigma v times sigma u cross sigma v is the unit normal vector on the surface S, then surface integral over S f dot n ds equals with surface integral over S p dy wedge dz plus q dz wedge dx plus r dx wedge dy. In the above relation, we replace f by its curl, and so we find surface integral over S curl f dot n ds. So here PQR are replaced by the components of curl F, that is del R del y minus del Q del Z, del P del Z minus del R del x, and del Q del x minus del P del y. And by Stokes theorem, this equals with line integral over del T P dx plus Q dy plus R dz. So we can write this as integral over del T P x dash t plus Q y dash t plus R z dash t dt. So this equals with line integral over del T inner product Fc, where C equal to del T is the curve on S whose parametric representation is given by Ct equal to xt, yt, zt. In an earlier module, we studied Green's theorem. In this module, we became familiar with Stokes theorem. Now we are going to show that Green's theorem can be considered as a special case of Stokes theorem. Let T be a bounded region in R2 and sigma from T to R3 be a map satisfying all the conditions laid down in Stokes theorem. We further assume that sigma t equal to S lies in the xy plane. So for points on S, the z coordinate is 0 and consequently dz is 0. We have already reduced that Stokes theorem can alternatively stated as surface integral over S curl F dot n ds equals with line integral over C f dot d alpha. Here C is the image of del T under the map sigma including the inherited orientation, and alpha is the parametric representation of C. Let f equal to mn0. Then we can represent mdx plus ndy as inner product of mn0 and dx dy dz, and curl F equals to minus del n del z, del m del z, and del n del x minus del m del y. As S lies on the xy plane, the unit normal n is identical to k, that is the unit vector along the positive z direction. Hence, curl F dot n equal to curl F dot k equal to del n del x minus del m del y. Consequently, surface integral over S curl F dot n ds equals to line integral over C f dot d alpha. This gives surface integral over S del n del x minus del m del y dx dy equals to line integral over C inner product of mn0 with x dash t, y dash t, z dash t dt, which is nothing but line integral over C m dx plus n dy. This relation is already known to us. It is nothing but the Green's theorem. One remark at this point, there is another way to represent this. If the curve alpha is reparameterized by arc length parameter and capital T denotes the unit tangent vector field along it, then we have d alpha equal to alpha dash s ds dt. This implies curl F dot k ds equal to line integral over C f dot alpha dash s ds. This equals line integral over C f dot t ds. Now we shall investigate for necessary and sufficient conditions for a continuously differentiable vector field defined on an open convex set to be gradient in terms of its curl. The result, let S be an open convex set in R3 and F equal to F1, F2, F3 be a continuously differentiable vector field defined over S. Then F is gradient on S if and only if its curl vanishes everywhere on S. Proof. We find that F is gradient on S if and only if for all x over S, del fi del xj equals with del fj del xi for every I and j from 1 to 3. This holds if and only if at each point of S, del f1 del x2 minus del f2 del x1 equals with del f2 del x3 minus del f3 del x2 equals with del f3 del x1 minus del f1 del x3 equal to 0. This holds if and only if at each point of S curl f vanishes identically. This ends the proof. In the above case, the Jacobian matrix of S is given by dfx equal to del f1 del x1 del f1 del x2 del f1 del x3. In the second row, f1 is replaced by f2 and third row f2 is replaced by f3 equal to SA for every x in S. Clearly, divergence of f equal to del f1 del x1 plus del f2 del x2 plus del f3 del x3, which is nothing but trace of the matrix df. In case f is gradient, the above 3 by 3 matrix A can be uniquely represented as A equal to half A plus AT plus half A minus AT equal to B plus C, where B is equal to half A plus AT, which is symmetric, and C equal to half A minus AT, which is skew-symmetric in nature. Now, the vector field F is gradient if and only if C equal to the 0 matrix of order 3 by 3. This holds if and only if we have written here the components of C. So, we have matrix with first row 0 minus curl f dot k minus curl f dot j, second row curl f dot k 0 minus curl f dot I, third row curl f dot j curl f dot I 0 equals to 0 matrix of order 3. This holds if and only if curl f dot I equals curl f dot j equals curl f dot k equal to 0. This holds if and only if curl f equal to the 0 vector field. The following theorem shows us a constructive method to find out a vector field once its curl is known to us, subject to certain conditions. Theorem: let S be an open rectangular parallelepiped in R3. Let F be a continuously differentiable vector field on S. Then F can be expressed as a curl of a vector field G on S if and only if divergence F vanishes everywhere on S. First, we assume that there exists a vector field G such that curl G equal to F. Then we find that divergence of F equals nabla dot F, that is nabla dot curl G, which is 0. Thus, the given condition is necessary. Next, let F equal to F1, F2, F3. Our task is to inquire the existence of a vector field G equal to G1, G2, G3 such that curl G equal to F. In such a case, we must have del G3 del Y minus del G2 del Z equal to F1, del G1 del Z minus del G3 del X equal to F2, del G2 del X minus del G1 del Y equal to F3. Now, to make our job easier, we first assume that G1 is the 0 scalar field and we search for G2, G3 satisfying the required conditions. In such a case, we must have del G3 del Y minus del G2 del Z equal to F1 minus del G3 del X equal to F2, del G2 del X equal to F3. From the last two relations, we have G3 XYZ equals minus integral x0 to x f2 tyz dt plus terms independent of x. Let it be f3yz, and similarly G2 xyz equal to integral x0 to x f3 tyz dt plus f1yz. Here both the integrations are performed along a line segment joining x0 yz and xyz. As S is a convex set for x0 yz in S and xyz in S, the line segment also lies inside S. Now, we make another assumption that f3yz is 0. Then del G3 del Y minus del G2 del Z equals del y of minus integral x0 to x f2 ty z dt minus del z integral x0 to x f3 ty z dt plus f1 yz. After some calculation, we find that this equals with f1 xyz minus f1 x0 yz minus del f1 del z yz. Here we have used that divergence of f is 0. Now we consider small f1 such that del f1 del z at yz equal to minus capital F1 x0 yz. So we consider f1 yz equal to minus integral x0 to x f1 x0 yu du. At once it follows that del g through del y minus del g2 del z equal to f1. Hence we have g1 equal to the 0 scalar field, g2 equal to integral x0 to x f3 ty z dt minus integral x0 to x f1 x0 y u du, and g3 equal to minus x0 to x f2 ty z dt. Clearly, we can check for this curl g equal to f whenever divergence f is 0. This completes the proof. Note, from our construction it is clear that such a vector field G is not unique. So a natural question is, once we find such a G, what are the relations between two such vector fields G1, G2 such that curl G2 equals with curl G1 equals F? We note that if F is any scalar field, then curl of grad F equal to theta. So if curl G1 equal to F, let G2 equal to G1 plus grad F. This implies curl G2 equal to curl of G1 plus grad F. By the properties of curl, this equals with curl G1 plus curl of grad F, but the second term vanishes identically, so we are left with curl G1. On the other hand, let curl G1 equal to F equal to curl G2. So curl of G1 minus G2 is the 0 vector field. This implies del hi del xj equal to del hj del xi, where h is G1 minus G2, and this holds for every I and j from 1 to 3. This implies h equal to G1 minus G2 is a gradient vector field. From the above discussion, it is clear that we can consider Stokes theorem as surface integral analog for second fundamental theorem of calculus. The above theorem may not be valid if the domain is not a rectangular parallelepiped. An example can be found in the book Calculus 2 by Tom M. Apostol. Irrotational vector field. A vector field is said to be irrotational if and only if it is continuously differentiable and its curl is the 0 vector field. Solenoidal vector field. A vector field is said to be solenoidal if and only if it is continuously differentiable and its divergence is the 0 scalar field. One note, in the statement of Stokes theorem, we assume that T is a simply connected region. The theorem can be extended to the case when T is multiply connected. Next, we shall study a result which relates a volume integral and a surface integral. The domain of integration is a bounded region in R3 and the surface concerned is its boundary. This is divergence theorem, which is also known as Gauss theorem. Let V be a convex solid in R3 whose boundary del V is an orientable closed surface S. We further assume that the surface S is smooth and N denote the unit outer normal vector field defined on S. If F equal to F1, F2, F3 is a continuously differentiable vector field on V, then we have volume integral over V divergence F dx dy dz equal to surface integral over S f dot n ds. The proof of the result. By proposition, F1, F2, F3 are continuously differentiable scalar fields defined on S. Let cos alpha 1, cos alpha 2 and cos alpha 3 be the direction cosines of n. The smoothness of S implies the smoothness of n and hence of the angles alpha 1, alpha 2, alpha 3. Now, divergence F is del F1 del x plus del F2 del y plus del F3 del z, and F dot n is F1 cos alpha 1 plus F2 cos alpha 2 plus F3 cos alpha 3. This means we are to prove that volume integral over V del F1 del x plus del F2 del y plus del F3 del z dx dy dz equals with the surface integral F1 cos alpha 1 plus F2 cos alpha 2 plus F3 cos alpha 3 ds. Now, in the relation we first put F2 equal to 0 equal to F3, then F3 equal to 0 equal to F1, and finally F1 equal to 0 equal to F2. Here 0 denotes the zero scalar field defined on an open set containing V union its boundary. We get the following three equations. Volume integral over V del F1 del x dx dy dz equals surface integral over S F1 cos alpha 1 ds and two similar equations. On the other hand, if we add these three equations, we can get the earlier one. Hence, the system of these three equations is equivalent to the earlier equation. Let us consider the set T equal to collection of points x, y, 0 such that x, y, z is in V. Clearly, T lies in the xy plane. Moreover, the convexity and connectedness of V assures the connectedness of T. We define two functions small l and small u over T as follows. Uxy is defined by the supremum of z such that xy is in T and xyz is in V, and Lxy is the infimum z where xy is in T and xyz is in V. Clearly, both these functions are well defined. Since del S is smooth, it follows that u and L are also so. Moreover, for every xy in T, Lxy less or equal to uxy. So, we have shown the surfaces SU and SL, where SU is defined by the collection of points xy uxy, where xy is in T, and SL is collection xy lxy such that xy is in T. Clearly, the surface S is a superset of union of SU and SL. One can easily check that every line through T parallel to the z-axis intersects V in a line segment joining the points x, y, lxy and x, y, uxy. Now, volume integral over V del F3 del z dx dy dz equals to double integral over T of integral Lxy to uxy del F3 del z dz dx dy. This equals with double integral over T F3 xy uxy minus F3 xy lxy dx dy. Now, del V is divided into following three parts based on the direction of the normal vector. First, on SU, the unit normal vector has non-negative z component. Secondly, on SL, the unit normal vector have non-positive z component, and finally on SH, which is SU union SL subtracted from del V, the unit normal vector is perpendicular to the z axis. Hence, on SU, cos alpha 3 is non-negative, on SL, cos alpha 3 is non-positive, and on SH, cos alpha 3 is 0. These three parts overlap on curves which are sets of content 0. Consequently, surface integral of f3 cos alpha 3 over s equals with the surface integrals of f3 cos alpha 3 over SL, SH and SU. Since the integral over SH vanishes, we have this equals with surface integral over SL f3 cos alpha 3 ds plus surface integral over SU f3 cos alpha 3 ds. Now, the parametric representations of SL and SU are the following. SL is given by xy goes to xy lxy and SU given by xy goes to xy uxy, where xy is from T. We denote the above two maps by sigma L and sigma U respectively. Thus, on SU, the unit normal n is codirectional with sigma x cross sigma y, and on SL, n and sigma x cross sigma y have opposite directions. Consequently, we find that surface integral over SU f3 cos alpha 3 ds equals surface integral over SU f3 dx wedge dy. This equals double integral over T f3 xy uxy dx dy. Similarly, surface integral over SL f3 cos alpha 3 ds equals with minus double integral over T f3 xy lxy dx dy. Adding the above two equations, we find that surface integral over S f3 cos alpha 3 ds equals surface integral of f3 dx wedge dy over SU minus integral of the same quantity over SL. So, this equals with double integral over T f3 xy uxy minus f3 xy lxy dx dy. This equals with triple integral over V del f3 del z dx dy dz. So, this is one of the three equations we are trying to prove. In a similar to, the other two can be proved. This completes the proof. We have already seen that divergence f and curl f depends on the components of f, and the components of f are functions of coordinates. So, it seems that change in coordinates will result in change in divergence f and curl f. But Stokes theorem and divergence theorem give results involving divergence and curl, but they do not involve components of the vector field. This shows that divergence and curl of a vector field are coordinate independent and hence are intrinsic in nature. Thus, while studying line integrals and surface integrals, we studied three theorems: Green's theorem, Stokes theorem, and finally divergence theorem or Gauss theorem. Comparing them, we find that first, Green's theorem related double integral with line integral. The curve of the line integral was the boundary of the region of double integral. Secondly, Stokes theorem related surface integral and line integral. The curve of the line integral was the boundary of the surface concerned. Thirdly, divergence theorem related surface integral and volume integral. The surface under consideration is boundary of the region concerned. So, in this module we studied Stokes theorem and divergence theorem. With this chapter surface integral comes to an end.